In this section, we're going to introduce the concept of polar coordinates. At this point, you have been through algebra and you've seen graphs of trigonometric functions. At this point, you're pretty good at graphing. However, now that we're pretty good at graphing the traditional way, let's take a look at a different way. Let's say you have a point right here. Where is that point? You say, well, it's on your paper. Okay, let's be a little more formal about it. Here's your XY plane. Where's the point? You say, oh, well, we just have to measure how far along it is along the x-axis. Maybe that's 1, 2, 3, 4. And maybe up this way, it's 1, 2, 3. So this is the point 4, 3. And you would be correct. That's exactly where that point is, 4, 3. On the xy plane, you can designate a location by telling how far left or right you are removed from the origin. That's your x-coordinate. And how far up or down removed you are from the origin. That's your y-coordinate. But there are other ways to go about this. Because if you were standing out in a field somewhere, if you were standing in a room, and you were standing right here, and I told you, you need to get to that point. And say, well, okay, I could walk 4 steps this way, and then 3 steps this way. But you probably wouldn't do that, would you? It's not how most people move throughout a room. That's not how most people move in space. You could, of course, do that. You would take 4 steps this way and 3 steps that way. Or you could do the other way around, 3 steps this way and 4 steps that way. But that's not the way most people walk. What you would probably do is say, well, I'm standing right here. What I want to do is I want to look in the direction that I want to walk. If you're like me, you're clumsy, you have to look in the direction. Like this. And then you would just walk straight there. Okay. But if these coordinates, 4, 3, are directions to get to this point, I can get to this point using a different set of directions. So does that mean there's a different set of coordinates? Absolutely, it's what it means. We just have to be careful how we designate these things. What we're going to do is we're going to take a direction. We want to face the direction that we're going in. Okay, well, to find a direction, I can use an angle. What we're going to do is, since we're at this point, we're using central angles in standard position. That's what we'll do. We'll say we want to walk along this line. Let's imagine that this line that we want to walk along is the terminal ray of a central angle in standard position. That is to say, the initial ray is the positive half of the x-axis. So the angle theta will give me the direction I want to walk in. Now I know which direction I want to go in. Now I just need to know how far to go. Okay, well then that's this distance here. We call this distance r. So whereas this point right here is a point where you have an x and a y, and that will get you to this point, there is another way to get to this point, and that is using an r and a theta. R is the distance you want to travel, and theta is the direction to get to that distance. Okay, but how on earth do you find that distance? Well, the good thing is, this is still the same point. We want to find a way of relabeling, but we're not actually moving the point. This point here, we know this distance because it's the y value of this coordinate. We know this distance because it's the x value of this coordinate. This is my x value, this is my y value. Oh, but now I have a nicely set up right triangle. I can use the Pythagorean theorem for this. So, remember our Pythagorean theorem? A squared plus b squared equals c squared for any right triangle. Here, the two short sides are our x and our y, so those will take the place of the a and the b. And c, our hypotenuse, is this distance that we want. It's what we're calling r. Okay, so r squared. X squared plus y squared equals r squared. Oh, well, in that case, I can go ahead and take the square root of that number to give me my distance. I get r is equal to the square root of x squared plus y squared. So right here, I could actually do that with these numbers. For my particular example, I could say, well, my r, my distance, is going to be the square root of 4 squared and 3 squared. Okay, that's 16 plus 9, that's 25. So the root of 25 is just 5. So here, our value r would be 5. Okay, what about our angle? Well, we have a right triangle. Here, this angle theta is what we want. And hey, look, I happen to know the x and the y ahead of time. Now, I know r, I can figure it out, but let's stick with x and y. Let's stick with the ones that we were given originally. Well, in that case, the x and the y are the opposite and the adjacent sides relative to this angle. That's tangent, isn't it? Here, the tangent of the angle theta is equal to the side opposite divided by the side adjacent of the angle, like this, like x over y, which means here I could take the inverse tangent to get our result. If I have the tangent of theta is equal to y over x, well, here my y is 3, my x is 4, then here I could take the inverse tangent. Theta is equal to the inverse tangent of 3/4, and I would, inverse tangent, and I would get, well, if I want an exact solution, I would get inverse tangent of 3/4. If I'm okay with an approximation, I grab one of these things and type that in. So right here, if I'm being precise, I can actually write inverse tangent of 3/4, and that'll work. I can write that right here. But if I'm okay with an approximation, I can say that's approximately, I'm in degrees here, so this would be 36 point, I'll just do 2 decimal places, 36.87 degrees. 36.87 degrees. And if you want to do this in radians, of course it works in radians as well. You just need an angle. So here, these coordinates, this r and this theta, are not designating a different point. This is still the same point that we started with, but it's labeled a different way. This labeling, using r and theta, is what we call polar coordinates. Here we can I don't know how to spell. Let's try that again. Coordinates. It's amazing how far I've gotten in my life without ever learning to spell. Polar coordinates. We have a few equations that help us convert back and forth between polar and our traditional rectangular coordinate system, our traditional x and y. You've seen 2 of them already. Here we have the tangent of theta is equal to y over x. Now, you might think, well, why don't you just write theta by itself? Can't you write theta is equal to inverse tangent of 3/4? Or I guess in this case, tangent theta is equal to tangent inverse of y over x. Why do you leave the tangent there? We actually do not want to write it as theta equals inverse tangent of y over x. Not because it's wrong exactly, but because it hides something that we need to highlight. We'll see that here in a little bit in our next examples. The other one we want to do here is we want to use the equation that we saw here. We want to use r squared equals x squared plus y squared. And again, you say, well, couldn't you use r equals square root of x squared plus y squared? Again, it's not wrong to write this, but it would kind of hide something that we want to highlight. And so we'll see that here again in our next examples. So I'm going to write it this way. And this is usually the way we write it. There's 2 more that we haven't seen yet, which you can very easily see from this triangle. Note here that if you take this x and this r, that forms the adjacent and the hypotenuse relative to the angle theta, respectively. So that means that the cosine of the angle theta is equal to our adjacent over our hypotenuse, our x over our r, and then you could multiply the r over this way. What that would give you is x equals, the x is not by itself, r times cosine of theta. And if you use sine instead of cosine, the sine of theta is equal to the side opposite over the hypotenuse, y over r. You could multiply the r to the other side, and you would isolate your y is equal to r sine theta. Like this. So these equations here are what are going to allow us to convert back and forth between rectangular coordinates and polar coordinates. You want to, basically you just want to memorize these, especially these 2. You see, are these 2 not important? They are, but you'll get more use out of these, and these will give you these. If you forget these, take this one divided by that one. Y over x equals, the r's would divide away, and you would get sine of theta over cosine of theta. Yeah, that's that one right there. Here, if you square both of these, and if you square both of these and add them together, you'll get this one. So these two will give you these automatically. All right, so at the very least, make sure you remember these, but ideally you should remember all four of them. All right, so let's see some examples here. Our first examples are going to serve some double duty here. They're going to show us how to use these equations here, but they're also going to show us visually how polar coordinates work. All right, so here we go. Let's say I have a point in the plane. Now, whenever I'm looking at a graph in x and y, on the xy plane, I'm used to seeing things as a grid. I'm used to seeing things this way. That's how graph paper looks like, right? If you ever have any graph paper, it's a bunch of little grid lines. And that's very useful for rectangular coordinates because you can follow the grid lines along the x-axis, along the y-axis to get to the point you want. But in polar coordinates, that's not quite how it works. You're not following the x-axis and the y-axis. You're following angles and distances. Okay, well, what do you mean distances? Well, when I say I'm 1 unit away, I don't mean 1 unit to the left or to the right. What I mean is 1 unit in some direction. So here, if I say I'm 1 unit away from this middle point, I'm somewhere on this little circle of radius 1. If I say I'm 2 units away from this point in the middle, well then I'm somewhere on this circle of radius 2. If I'm 3 units away from this point in the middle, then I am somewhere on this circle of radius 3, and so forth and so on. So my graph paper isn't going to follow distances left, right, or up and down. It's going to follow distances out, radiating outward from this center point. So here, if I'm going to draw grid lines, I'm not going to draw vertical and horizontal lines. I'm going to draw lines like this. Well, not only am I going to have to follow distances, that's what my R is, I'm also going to have to follow an angle, theta. Oh, well, we already know how to graph something like that. That's the unit circle. What we want to do is we want to draw some lines that designate, that represent the different angles that we're going to designate as our directions. So here, you can, of course, draw as many lines as you need to and to track whatever angles you need. But it's conventional to start with the ones that you're familiar with, the 30 degrees, the 45 degrees, the 60 degrees, the 90 degrees, the ones you're familiar with off the unit circle. This right here is what a grid would look like for graphing things in polar coordinates. And that actually exists. You can actually find this. You can buy polar graph paper, or you can find some online. Here, this one that I found is marked off in degrees. However, in fact, here they mark these in radians. Sometimes they're marked in degrees, sometimes they're marked in radians, sometimes they have both. But this is an example of polar graphing paper, something like this. You say, okay, so that's how we're going to graph. You keep saying this point in the middle. Yeah. Don't you mean the origin? I mean, that's what it's called, right? I remember that from algebra. It's called the origin. Well, in the xy plane, it's called the origin. And yeah, we're still technically on the xy plane, but we're not using x and y anymore. We're using r and theta. So this point in the middle has a name. You say, not the origin? No, this is called the pole. That's why these are called polar coordinates. They're centered around the pole. You say, well, what kind of name is pole? Why on earth would you call it that? Well, take a look at another pole. Here I have a small model of the Earth, little globe. Does that look familiar? There's your South Pole. Here we're in Antarctica. Here's your South Pole. North Pole also, but that's more cluttered, so let's do the South Pole. Here's your South Pole. Radiating outward from the South Pole, you have these lines of latitude, or the lines of longitude rather, and then you have these little circles here, 1, 2, 3. These circles are your lines of latitude. Oh, but that's what this is. So we call this the pole because it really is just the pole. You can imagine this as being like a sphere, like a ball. So from the pole, you radiate outwards. You measure your angle along your lines of latitude, your lines of longitude, and you measure your distance along your lines of latitude. First line, second line, third line, and so forth. The naming convention comes from nautical tradition, from navigating ships. So here we call this the pole, and hence these are polar coordinates. So now if I have a point out here, for example, I have this one right here. This point is 3 units away from the origin, from the pole. 1, 2, 3 units, so our r would be 3, and it's following along the angle of, well, let's see, that's 0, that's 30 degrees, 45 degrees, 60 degrees. So right here, this would be 3, 60 degrees. Just like in rectangular coordinates, we do x and then y. In polar coordinates, we always do r first and then theta. And of course, here you can also write this as 3, pi thirds, if you're using polar instead of polar coordinates in radians rather than in degrees. You say, oh, so I guess there's 2 ways of writing each of these. One's in degrees and one's in radians. Yeah, that's right. But there's more than just those. You say, what do you mean? Well, that goes back to my statement earlier about theta and r. I didn't write theta is equal to y over x. I didn't write theta is equal to inverse tangent of y over x. I wrote tangent of theta equals y over x. Aren't those the same thing, though? And likewise over here, I wrote r squared equals x squared plus y squared. Why didn't I just write r equals square root of x squared plus y squared? All right, why do I write it this way? It's because if I write it the other way, if I write it with just the r or just the theta isolated, it's a little misleading. If I write r equals square root of x squared plus y squared as my formula, that makes it sound like r is always positive. After all, if you square 2 things, they're positive, and then the square root of a positive number is a positive number. You say, well, r is a distance, right? So shouldn't it always be positive? Well, yes, but no. Here, I can write this a different way. All that matters is that I'm facing this direction and going 3 steps forward. All that really matters is that I end up right here. So look what I can do. I can go 360 degrees all the way around, and then another 60. That's a total of 420 degrees. But you know what? Even though that's a different number, I'm still facing the way I want. And I could go forward 1, 2, 3 steps. So another way to write this is 3, 420 degrees. Or I could do it in radians, but I'm going to stick to degrees right now. I could go backwards. Instead of going forward 60 degrees, I could go backwards 300 degrees. And I would still be facing the same way. So here this would be 3, negative 300 degrees. And that would also work because going backwards 300 degrees would have me facing the right way. So here, that's why we don't write theta is equal to inverse tangent of y over x. Because if we write that, you're going to assume that it's just whatever the calculator tells you. Oh, inverse tangent of 4/3 is equal to 36.87 degrees, and that's it. That's the only answer. But by writing it this way, it serves as a reminder that, oh yeah, tangent of theta is periodic, as we've learned in previous chapters. If it's a periodic function, it happens over and over and over again. We write it this way to serve as a reminder. This isn't unique. So, unlike rectangular coordinates, where 4, 3 is the only way to write this, and that's it, that's the only way you ever could write this, in polar coordinates, you do not have a unique representation. So here we'll put this as a note. Note, polar coordinate representations are not unique. There's different ways of getting to the same point. You say, okay, so I guess as long as I go forward or backwards, as long as I end up facing that way, then it'll be 3, whatever angle I get. Well, yeah, that's true. But you could do it another way. Because think of it this way. What if instead of stopping at 60 degrees, I kept going? You say, go all the way around? No, just half. From 60 degrees, let's say I do half a spin. Over here, 60 degrees plus 180, that's 240. 240 degrees. You say, well, yeah, but now you're facing the wrong way. Well, yeah, it's true, I am facing the wrong way. But I could walk backwards. If I were standing right here and facing this direction, to get to the point I want, I could just walk backwards. So here, I could also say, well, if my angle is 240 degrees, I can just go backwards. Well, how do I say going backwards? Well, r is how far I'm going, and traditionally, if you want to go in the opposite direction, you just call that a negative. So here I could say negative 3, 240 degrees. That's why right here we don't say r equals square root of x squared plus y squared, because that assumes that r has to be positive. But you could use a negative and still get to the same point. Face the wrong way and then walk backwards. Who says two wrongs don't make a right? Huh? Two wrongs may not make a right, but two negatives make a positive. So here, you could go this way and then walk backwards. And in fact, you could do the same trick that you had up here. You could go backwards this way. Instead of going forward 240 degrees, I could go backwards 140 degrees. Sorry, 120 degrees. And if I go negative 120 degrees, I'll still be, I went the wrong way. I went backwards, but whatever. I'm still facing the way I want. Well, no, you're not. You're facing the opposite of the way you want. Okay, fine, then walk backwards. And every single one of these will get you to this point right here. So very clearly, polar coordinates are not unique. And the reason we don't write this as just theta or just r is to hopefully remind us of that fact. Oh yeah, I have to do something. Oh yeah, that means I can have more than one answer. Oh, I have to do something. Oh, and that's a periodic function. Yeah, I can get more than one answer. So be mindful of that. Polar coordinate representations are not unique. Okay, but if there's so many different ways of writing it, how do I pick the right one? Or does it just straight up not matter? Well, yeah, it actually just doesn't matter. However, it can be really, really cumbersome and really inconvenient if everyone's writing things a different way. Even though all of these are the same point, it gets really awkward if we're all doing math differently. It's easier if we all have something agreed upon. So, although all of these are valid, there is one standard choice. This is called a convention. It's not right because it's the only right way to do it. It's right because we've decided, you know what, let's just go ahead and do it this way. Even though multiple ones are valid, we're going to stick to this one. So by convention, that is to say, because we've agreed upon it, I don't know how to spell. Let me see. That should be E, right? Yeah, that sounds right. Convention. Oh, I hope that's right. Oh, well. Convention. Yeah, that looks right. So by convention, we want R to be positive or equal to 0. Now, we will sometimes break convention for convenience. Convention is just a strong suggestion. Nothing says we have to stick to this. It's just that unless there's a reason to do otherwise, we'll stick to this. But if there is a good reason to do something else, we'll do something else. But the normal choice, if there's no other reason to break it, is R should be positive, and theta should be between 0 and 2 pi. It's okay if it's equal to 0, but it shouldn't equal to 2 pi. So here, although all of these, and that's in radians, if you want to do it in degrees, that's going to be between 0 and 360 degrees. Like this. So by convention, either of those is what we're going to use. So here, although all of these are perfectly valid, if you were to ask what is the one you are going to use, which is the one you prefer to use for computation, for theory, for anything, you're going to pick one of these two. And again, the choice between those is, do you want to do radians or degrees? All the rest of these are not wrong, but unless there's a good reason why we need to use these, we're going to stick with these. So this is the conventional choice. Okay, now with all that said, let's get to an actual computational question. Our question here is, this point, regardless of which way you've written it, could also be written in xy coordinates. The question is, convert 3 comma, and I'll use the degrees, 3 comma 60 degrees into rectangular coordinates. That is to say on the xy plane. Okay. So here we can use our equations here. We know an r, we know a theta, so we can plug those in to get x and y. So let's see here. X is equal to r cosine of theta. That is to say it's 3 cosine of 60 degrees. That is to say it's 3 times. The cosine of 60 degrees is a half, and 3 times a half is 3 halves, 1.5, however you want to say it. I'll say 3 halves. Y is equal to r sine of theta. That's equal to 3 sine of 60 degrees, which is 3 times. The sine of 60 degrees is root 3 over 2. And when we multiply those, we get 3 root 3 over 2. We really don't want to write this as a decimal, because if we write this as a decimal, we're going to approximate. We're going to round it. And here we want the exact point. So here, our point 3, 60 degrees in rectangular coordinates would be our x is 3 halves, and our y is 3 root 3 over 2. That doesn't change the point. It's the same point. It's just labeled a different way to get to that point. You would go 3 halves of a step this way and 3 root 3 over 2 steps this way. We can, of course, go forward or backwards as needed. Another example. Here we took a polar point and turned it into a rectangular. And we took a rectangular and turned it into a polar. We've seen both ways, right? Rectangular became polar. That was our very first example where we started. And then here we've seen polar back to rectangular. Okay? So that we don't have to keep flipping back and forth, let me just write the equations over here. Tangent of theta is equal to y over x. R squared equals x squared plus y squared. X equals r cosine theta. And y equals r sine of theta. So try the following 2 exercises. The first one, you're going to go ahead and convert. And we're going to take the point 5, 12 into polar coordinates. Obviously, if I'm saying convert to polar, this must be rectangular. And then the other example, go ahead and give this a try. You're going to convert. Let's do 6 times, let me do this one in radians. I'll do 6 comma 3 times pi over 4 into rectangular coordinates. Go ahead and pause the video, give it a try, just like the 2 examples we've already seen. And once you have a result, go ahead and unpause and we'll go through it together. All right, so if we're converting these into polar coordinates, that must mean these are rectangular. So this is an x and this is a y. Okay, so the tangent of the angle theta is equal to y over x, which is 12 over 5. Okay, so that means that theta, we're going to take inverse tangent of 12 over 5. Okay, let's see. So if I take the inverse tangent of 12 over 5, I get this answer here, approximately 67.38 degrees. Now you got to be careful, because remember, inverse tangent has more than one solution. So we have to check 2 things. First of all, we want to check to make sure we're facing the right direction. Here, 5 comma 12 means you went 5 units this way and up 12 units this way. You're going to end up in the first quadrant. 67 degrees, yep, that's in the first quadrant. If you end up with a value that is correct, that does point you in the right direction, cool, you're done. If not, I'll show another example of what to do in that situation. We'll see that here in a little bit. But for now, this works out just fine. Okay? The other thing you need to check is make sure that you fall under the convention that we set earlier, and that your theta in radians is between 0 and 2 pi. Yeah, that is between, we're doing degrees. Is between 0 and 360 degrees, which, yes, that is between 0 and 360. So, yes, that does meet our convention, and yes, that does point the right way. Okay, so that's our theta. The other thing we need is we need r. Okay, well, r squared equals x squared plus y squared. That is to say it's 5 squared plus 12 squared, which is 144 plus 25 is 169. And so r is equal to plus or minus, because to get rid of a square, you have to take the square root, and there's two different square roots you could take, plus or minus the root of 169, which is plus or minus 13. But again, that's, although those are both possible answers to this equation, but we do have to follow our convention, and that is, oh, don't forget, r is supposed to be what? R is supposed to be positive. So here, although both of those are possible, the one we want is the positive one. So if you were facing this way, you would go forward 13 units. So in the end, our answer would be, you put your r first, that's 13, and then your theta. If you're writing an exact solution, you write this. If you're taking an approximate solution, you write this. Whatever is appropriate for the example, for the question asked. And there's our result. Now over here, we want to convert this back to rectangular coordinates. All right, so if the point we want to convert is in polar, then this must be your r and this must be your theta. So that means that our x is r cosine theta, which is 6 cosine of 3 pi fourths. And y is equal to r sine of theta, which is 6 times the sine of 3 pi fourths. Okay, well, the cosine of 3 pi fourths, that's negative root 2 over 2. And the sine of 3 pi over fourths, that's positive root 2 over 2. 6 divided by 2 is 3, times our negative root 2, that's negative 3 root 2. Here it's the same thing, but with a positive. And so we get our result. Converting into rectangular coordinates, we end up with our x is negative 3 root 2, and our y is positive 3 root 2. Just like that. Okay. Before we go on to anything else, let's do one more example just like this, except let's see what happens if our angle is not cooperating the way we want it to. So for our last example of this type, let's go ahead and convert, let's do negative 6 and positive 8. Let's convert that into polar coordinates. Okay, so this is going to start off the same. We're going to take tangent of theta is equal to y over x, which is 8 over negative 6. Negative 8/6. Okay, so now here, you would say theta is equal to the inverse tangent of negative 8 over 6. If you want to reduce that to negative 4 over 3, that's good, but we're going to punch this into a calculator anyway. So here we're going to take the negative 8/6, and I'm going to take the inverse tangent. And notice that I get negative 53.13 degrees. Okay, negative 53.13 degrees. But look what happens if I do that, if I graph that. Negative 53.13 degrees. Remember, negative means your angle's going counterclockwise, so it's going this way. This is 0. This would be negative 90, negative 180. Okay, so negative 53 is between 0 and negative 90. So somewhere this way. Okay, but negative 6, positive 8 in rectangular coordinates means you're going to go to the left and up. Your x is negative, your y is positive. Notice that your angle is wrong. You're facing the wrong way. Well, why is that? Well, if you think back to tangent, remember that the range of the inverse tangent is only between negative pi over 2 and positive pi over 2. Recall, f of x equals inverse tangent, or some people say arctangent of x, has a domain that's from negative infinity to infinity except at the asymptotes, but the range, sorry, I said that wrong. The domain is from negative infinity to infinity, but it has a range that is only between negative pi over 2 and positive pi over 2. Or if you want to do it in degrees, that's negative 90 degrees and positive 90 degrees. So you can only ever get stuff over here. So if your point is either in the second or the third quadrant, your angle will be wrong. You say, okay, so that's not the right formula? Well, you just have to flip it. You have to go to the other side. So if negative 53 is wrong, it's not that it's not that you're completely wrong. It's just that you're facing the wrong way. So here what you need to do is you need to, again, to fit your convention, you want your angle to be between 0 and 360. You're just going to add your 180. So our angle is negative 53.13 degrees plus 180 degrees. You just have to do the half turn so that you're facing the right way. So that gives us that plus 180, and that gives you negative 126.87. 126.87 degrees, like that. So that would be our angle now without a negative. Okay. Okay. Now what about our distance? Well, let's see. R squared equals x squared plus y squared. That's going to be negative 6 squared plus 8 squared. That's 36 plus 64. That's 100. And so r squared equals 100, meaning that r is equal to plus or minus 10. But again, our convention is we want the positive one. So unless there's a reason we need to choose the negative one, we're always going to choose the positive one. And here, since your angle is 126 degrees, you are facing the right way, so then you would just go forward. So here we would end up with r is positive 10. Right, we don't have the negative one here because we want the positive one, comma, and then you would either write inverse tangent of negative 8 over 6 plus 180 degrees. Right, you would literally write this plus 180 degrees. Or if you want the approximation, which we're going to be good with that, we're going to write just our 126.87 degrees. So be mindful of that fact. Whenever you do this, if ever you're finding an angle and the angle is going to fall either in the second or the third quadrant, the inverse tangent will be wrong. But you can always fix it by just adding 180 degrees. Or if you're in radians, you would just add pi radians. And there we go. Okay. Finally, the last type of example we're going to look at. Here we've been seeing converting points to points. Here's a point in polar coordinates converted to a point in rectangular coordinates. Here's a point in rectangular coordinates converted into polar coordinates. But doing things point-wise, although it is sometimes necessary to look at what happens to a single point, is often not what we want. We often don't worry about individual points. We care about entire curves. We care about entire functions. So for our last set of examples, let's take a look at not converting individual points, but entire equations. Let's convert the rectangular equation and we'll do x squared minus y squared equals x to polar coordinates. All right, so here we go. We're still going to use the same information we did previously. We're still going to use this. In fact, let me write it over here so we don't have to flip back and forth. We're going to continue to use tangent of theta equals y over x, r squared equals x squared plus y squared, x equals r cosine theta, and y equals r sine theta. All right, so here we go. Anytime you see an x, you can simply rewrite it as r cosine theta. So this x and this x become r cosine theta. I am going to square, but let me square all at once. So let me not write it just yet. I'm going to say r cosine theta. My y, I'm going to replace it with r sine theta. And again, this x is r cosine theta. Okay. So this x is being squared minus this y is being squared equals this x doesn't have any power on it. Just leave it like that. Okay, well, when we square a set of, when we square a product, we can simply distribute the square across each of these factors. So this would be r squared cosine squared of theta minus r squared sine squared of theta is equal to r cosine theta, like this. Now, one thing I noticed right here is that r squared is a common factor. right here we have finished, technically. The question was to convert into rectangular. To convert from rectangular into polar. We've done that. We have finished by writing it in terms of r's and thetas. However, just like in rectangular coordinates, you don't usually leave equations just however. Usually you at least try to write it as y is a function of x, or maybe sometimes x is a function of y. Here we at least try to write it, if possible, as r is a function of theta, or theta is a function of r. Usually r is a function of theta. So here what I'm going to do is I'm going to, although I'm technically finished, let's see if I can't simplify this. On the left side, I notice that I have r squared as a common factor. So I'll factor that out. Looks like that. Okay, so now here we recognize the double angle formula for cosine. So this is r squared cosine of 2 theta equals r cosine of theta. And then, yeah, I guess this one we can't really solve for one variable, can we? So here we did simplify at least. And then at the very least, we'll write it in this form where we'll put everything together. We'll write this as r squared cosine of 2 theta minus r cosine of theta equals to 0. Okay. Again, technically all of these are correct. But just like with any equation in rectangular, in polar, you want to simplify as much as possible by combining like terms, combining any, getting rid of anything that cancels out, factoring out common factors, and things like that. So here, this equation in the rectangular form would become this equation in the polar form. Okay? And really, we just started by replacing all the x's with r cosine theta and all the y's with r sine of theta, and then simplifying as much as we could. And then for our next example, we go back the other way. Let's convert the polar equation we'll do r equals 5 cosine theta to rectangular. Okay. Again, using these. What we want to do is we want to replace any instance of r cosine of theta with x and any instance with r sine of theta with y. But it has to be exactly like this. Here you might notice I have cosine of theta. And you say, oh cool, that'll be your x. No, not quite, because you're missing an r. Now some people fall into the trap of thinking, well, r is equal to 5. There you go, there's r cosine theta. But it doesn't work that way. It has to be an r. It has to be an actual variable. You can't say r is equal to 5. R has to be just r. You say, well, then there's nothing you can do, right? Well, as it's currently written, no, there's nothing we can do. However, we can modify this. Because after all, it's an equation. Whatever we do to one side, as long as you do the same thing on the other side, it's a perfectly valid operation. So here, I would like to have an r multiplied times this cosine of theta. Okay, so go ahead and do that. Go ahead and put in an extra r. That's fine as long as I do the same thing on the other side. So now I've got 5. This r cosine of theta is replaced by just an x. You say, well, what about on this side? Well, r times r is like saying r squared. Oh, but we happen to know what happens to r squared. R squared is x squared plus y squared. And that's it. Here, we might try isolating. We might try solving for x or y. We might try simplifying. But right away, we recognize this as, oh, this looks like it's going to be a circle, right? Yeah, and circles aren't functions, at least not of x or y. So here, we, just from remembering some stuff from algebra, we realize, oh yeah, we're not going to be able to solve for x or y here, so that's the best we can do. So you try to simplify as much as you can, but recognize that some things just don't simplify past a certain point. Right, so go ahead and give this a try. That's our last examples here for this section. Go ahead and convert from rectangular to polar. Let's go ahead and convert, let's try x squared plus y squared equals 4y to polar. And also go ahead and try to convert. Go ahead and try to convert. Let's do r equals 2 times the secant of theta. All right. Again, you're using these. And go ahead and pause the video, give it a try. And once you're done, go ahead and unpause and we can go through them together. All right. So here, anywhere we see an x, we can replace that with r cosine theta. Anywhere you see a y, you can replace that with r sine theta. But don't let that blind you to the other two. These two are the ones we use most often to convert to polar. But notice right here, x squared plus y squared is already just r squared. All right, so let's just go ahead and do that. Why bother going through the longer process when x squared plus y squared is already just r squared? Here, 4 times my y, well, that I can replace with r sine theta. Okay. All right, and well, nothing really combines here. This is a square and this one's not. So if you leave it like this, that's perfectly fine. However, a lot of times we care to write things back as, we care to rewrite things so that everything's together in one side of the expression. So here we write r squared minus 4r sine of theta equals 0. Here, some people like to write it so that they factor out the r, so they get r times r minus 4 sine theta equals 0. That's kind of unnecessary, but some people like to write it that way. Here, really, either of these would be acceptable. For this one, you might get a little worried when you think, oh, secant. Secant doesn't appear anywhere in here. No, but cosine does. Here, I can go ahead and multiply both sides by cosine of theta. Here, cosine of theta. And the reciprocal identity is that the secant of theta is the reciprocal of the cosine of theta. So multiplying these together gives me just the number 1. So this becomes r cosine theta equals 2 times 1. Right? All of this becomes 1. And now r cosine of theta is your x. So here you get x equals 2 times 1, which is x equals 2. Here you can kind of see one reason why we like converting from rectangular to polar or polar to rectangular. Some equations are just easier in one form or another. Notice right here, this equation involved the trig function. Here it's just a constant. Over here, it requires you to have the sum of squares equals to a function of y, whereas over here it looks almost like a polynomial. So one reason we like converting from one form to another is sometimes one form is just easier to work with. Right? So if, for example, the question was, instead of converting, the question was graph the equation r equals 2 secant of theta, that would be hard. Plugging in different values of theta, getting different values of r, grabbing one of these polar coordinate grids, and then actually plotting individual points to get your graph, that would be hard. But if you then realize that that's just the same as saying x equals 2, oh, that's a much easier. X equals 2 is just a vertical line that crosses through the x-axis at 2. So this would be our graph here. So we can always take one form, and if it's just easier in another form, well, then just deal with it in that easier form. In the next section, we're going to take a look at how to graph polar coordinates in general, and that actually is one way to do it, and that is, well, maybe we can convert. But if you can't convert, or if you can but it's not any easier after you convert, then we'll see other ways of graphing in polar coordinates. But we'll see that in the next section. In the meantime, that's it for this section. If you have any questions, comments, problems, please make a note of those and reach out, and I hope you all have a nice day.